Hey guys, today's video is on Diffusion Tensor Imaging, or DTI. This is a subset of diffusion weighted imaging, or DWI, which we covered in a previous video a few years back, and you may want to review if you're a little rusty. For those who want to march on, a brief 2-minute summary. Diffusion weighted imaging is used to determine if there is diffusion restriction or limited molecular movement in regional tissues. This analysis is performed with identical but opposite strong magnetic gradients applied sequentially after the radio frequency pulse. If there is normal Brownian motion or no diffusion restriction along the direction of the applied gradient, the hydrogen protons in the molecules will move in between the two pulses and therefore will dephase or not spin together, weakening the NMR signal. However, if motion is limited along the gradient direction, the hydrogen protons in the local molecules remain in place between the two opposing gradients, experiencing equal and opposite local magnetic fields and effectively rephasing the protons, producing a strong NMR signal. But remember, we're talking about a 3D volume of tissue. Since this only determines the diffusion restriction along the applied gradient's direction, a series of 3 opposing gradients in the X, Y, and Z planes are necessary to determine if there is complete diffusion restriction in the local tissues. Diffusion-weighted imaging is the most sensitive MRI technique to determine acute stroke in the brain where the injured tissues swell and reduce molecular movement within minutes after injury. However, this is a binary analysis. Diffusion-weighted imaging can tell us either yes, there is diffusion restriction, or no, there is no restriction. It really can't give us any information about the direction of molecular movement. This beautiful image, on the other hand, was obtained with diffusion tensor data. The left shows the diffusion tensor information displayed using a tractography algorithm and basically maps out the course of the neuronal axons in the brain. The right image is simply a 3D model of the brain as a reference to show the orientation of the diffusion tensor image. The direction of flow is encoded in the color of the tracks with up and down blue, front to back green, and left to right red. So, for those who just wanted a quick definition of what is a diffusion tensor image, this is it. You may want to stop here. For the adventurous and scientifically inclined, the rest of this video will describe how we actually obtain the diffusion tensor information and what options we have for displaying the same. First, we need to go over a few definitions and mathematical concepts. Let's start with the definitions. Scalar, vector, and tensor. If I tell you I know a guy who is 6 feet tall, I am giving you an absolute number of my buddy's height. I'm not telling you if he's lying down, standing up, or maybe even doing a handstand. He's just 6 feet tall. That measurement is known as a scalar. Just as if I told you it's 75 degrees in the house, or I weigh 165 pounds, all scalars. However, if I tell you I'm traveling 35 miles an hour heading southeast across the desert in my monster truck, I can represent that with a vector where the arrow point indicates my direction of movement, and the length of the arrow shaft indicates my speed. So the vector provides both a scalar value, my speed, and the additional directional information. In 3D space, this vector, which we'll label M for monster truck, can be represented by its 3 scalar Cartesian components on the X, Y, and Z planes, MX, MY, and MZ. Now, what if we have to consider multiple vectors in 3D space acting on a single system? How do we represent that mathematically? That's where tensors come in. Let's superimpose a 3D cube over our Cartesian coordinate system. As you can see, each of the 3 visible faces of the cube now corresponds to each of the major axes of the coordinate system, x, y, and z. A vector on each of the faces is now represented by its own coordinate system in 3D space, and we can mathematically model each vector using the layered coordinate system as we did before, but now with 2 variables defining the vector components as follows. Starting with the x face of the cube, this vector would be described as txx, txy, and txz. The y face would be tyx, tyy, and tyz. Finally, the z face would be tzx, tzz, and TZY. As you can see, with 3 vectors represented by their 3 variables in 3D space, there are a total of 9 components which can be arranged in a 3x3 matrix like this. Each column is one of the 3 vectors, and each row now represents the x, y, and z components of the whole system respectively. This matrix is the mathematical representation of the tensor. Again, with each component represented by 2 variables, this is a second-order tensor. In fact, the single vector and scalar measurements are also considered tensors, with the vector a first-order tensor and the scalar a zero-order tensor. Now I want to go back and get into some specifics about our second-order tensor matrix. As you can see, the 3x3 matrix with its 9 components is symmetric about the main diagonal with 3 components on each side of the diagonal line. The diagonal components themselves are the 3 axes perpendicular to their respective planes, txx, tyy, and tzz. Ultimately, what we want to do is to collapse the entire tensor system down to the main coordinate axis by summing up all of the individual vector components in the system and producing a series of characteristic vectors centered on the main Cartesian coordinate system. With the tensor concept, we can accomplish this goal mathematically. So let's define some of these mathematical concepts: matrix multiplication, eigenvalues, eigenvectors, and matrix diagonalization. We'll start with matrix multiplication. Not just any 2 matrices can be multiplied. There are some restrictions. Most importantly, the number of columns in the first matrix has to equal the number of rows in the second, and I'm going to show you why in a moment. So let's take our tensor matrix with 3 rows and 3 columns and multiply it by a 3D vector which can be represented by this 3x1 matrix with 3 rows and 1 column. To confirm that these 2 matrices can be multiplied, look at the inner 2 numbers, which represent the columns of the first matrix and the rows of the second. If these 2 are the same, which they are, these matrices can be multiplied. In addition, the outer 2 numbers, representing the rows of the first and the columns of the second, will give you the resulting matrix size after multiplication, which, in this case, will be a 3x1, another vector. To multiply this tensor with the vector, we multiply each component of the first row of the tensor with each corresponding component of the vector column and add all these values up to give us the first component of the new matrix or vector. We do the same thing with the second and third rows of the tensor to give us the middle and bottom components of the new vector respectively. So let's put some actual numbers in our matrices to see how this works. 2 times 1 equals 2, 3 times 1 equals 3, 0 times 1 equals 0, 2 plus 3 plus 0 equals 5, the first component of our new 3x1 matrix or vector. Going to our second row, 3 times 1 equals 3, 2 times 1 equals 2, 0 times 1 equals 0, 3 plus 2 plus 0 equals 5, the second component of our new matrix. Finally, multiplying the third row, 0 times 1 equals 0, 0 times 1 equals 0, and minus 2 times 1 equals minus 2. 0 plus 0 minus 2 equals minus 2, the third and last component of our new matrix. So you can see that multiplying our second-order tensor by a vector gives us another vector. Now I want to compare these 2 vectors graphically. The original vector is made up of the 3 unit vectors in the x, y, and z axis of the Cartesian coordinate system. The resulting vector after multiplication is longer, points in a different direction, and really has no mathematical relationship to the original vector. So let's go back to our original matrix multiplication. I'm going to change the z value of the original vector to 0. I'm not going to go through the entire multiplication process again. You can stop the video and check it if you want, but that change gives us the following result. Again, let's compare the 2 vectors graphically. The original vector lies in the xy plane and is composed of the unit vectors on the x and y axis and therefore looks like this. The resulting vector also lies in the xy plane, points in exactly the same direction as the original, and is basically 5 times longer than the first. Going back to our new matrix multiplication, we can factor out a 5 from our multiplication product and rewrite the resultant vector as a scalar value 5 multiplied by our original matrix 1, 1, 0. In this special situation, when we multiply a matrix by a vector and the result is the same vector multiplied by a scalar, the vector is known as an eigenvector and the scalar number is an eigenvalue. Eigen is German for own, and not the verb own like I own that car, but the adjective or pronoun, that's my own. It can also be loosely translated as inherent or characteristic. Thus, the eigenvector is one of the characteristic vectors of our tensor matrix, and the eigenvalue is the scalar multiple of the eigenvector. Determining the eigenvalues and eigenvectors is the mathematical equivalent of collapsing our second-order tensor to the characteristic vectors of the original Cartesian coordinate system. So now it should be easy to understand the formula definition of eigenvalues and eigenvectors, which state that if we multiply a square matrix, such as our 3x3 tensor, by a vector, and the result equals a multiple of the original vector, the vector itself is an eigenvector or characteristic vector of the original tensor, and the scalar value is one of the eigenvalues of the tensor itself. The last mathematical concept I want to present before we get back to diffusion tensor imaging is matrix diagonalization. I just showed you one of the eigenvectors and corresponding eigenvalues of our simple tensor. There are actually two more, as for any n by n matrix, there are n eigenvalues and eigenvectors. So our 3x3 tensor has a total of 3. Diagonalization is the mathematical construct that allows us to actually calculate these eigenvectors and eigenvalues. The math is a little complex, and I'm not going to go into any detail of the actual calculation, as there are plenty of good videos on YouTube if you're interested. Bottom line, at the end of the calculation, all of the off-diagonal entries of our matrix become 0, and the 3 remaining numbers on the diagonal line are the 3 eigenvalues of our original tensor. These values can then be used to calculate the actual 3 eigenvectors. Okay, enough math. Let's go back and look at molecular diffusion in our brains. Our brains are made up of trillions of individual brain cells or neurons that communicate with one another to create and store memories, control movement, allow us to see, speak, hear, and basically interact with and interpret the world around us. Each individual neuron has a cell body that contains the nucleus and all the cellular organelles that keep the cell alive. The multiple dendrites directly off the body are short extensions that receive signal input from other neurons, and a single large extension off the body is called the axon, which carries the neuronal output. The axon is covered in a myelin sheath, a fatty insulator that helps propagate the electric signal down the nerve into the terminal branches of the axon. These terminal branches form junctions with other neurons, which in turn will fire when stimulated by the electric signal from the first neuron. Zooming into the cell body, will represent the hydrogen protons associated with the water molecules within the cytoplasm with these blue spheres. Because of the round shape of the cell body, the water molecules with their associated hydrogen atoms are free to move in any direction without restriction. This type of symmetric movement is called isotropic diffusion. Contrast that with the movement in the axon. Because of the cylindrical geometry of the axon, movement of the water molecules and their hydrogen atoms is asymmetric, predominantly moving along the axis of the axon channel, which we'll represent with this large vector. There is also some limited movement of the hydrogen protons to the periphery of the axon channel, which we can represent with these two smaller vectors. This asymmetric movement of the hydrogen protons is called anisotropic diffusion and, as you can see, can be represented by these 3 orthogonal vectors that look just like our 3 eigenvectors and eigenvalues from our tensor we described earlier. So in diffusion tensor imaging, we obtain a sufficient number of gradient directions to determine the tensor components of our matrix. Based on the 9 components of the second-order tensor, we would assume that we need a minimum of 9 gradient directions to acquire all the necessary data. However, if we assume the axon bundles are symmetric, then the 2 minor eigenvectors should be identical in size. With this assumption, a minimum of 6 gradient directions are necessary, essentially eliminating one base vector. We can then use the mathematical techniques described previously, mainly matrix diagonalization, to determine eigenvalues and eigenvectors, which indicate the major and minor directions of diffusion movement down the axon. Couple more things before we wrap this up. First of all, if we take our tensor eigenvectors and rotate them on the main axis of the large vector, you can see the path maps out an ellipsoid. The long axis of the ellipsoid graphically depicts the main direction and relative rate of anisotropic diffusion, with the short axis depicting the minor direction of diffusion. Contrast that to the tensor ellipsoid representation of isotropic diffusion in the cell body. Let's first hide the nucleus. In this location, since the rate of diffusion is equal in all directions, the isotropic diffusion can be represented as a symmetric sphere. Tensor ellipsoids are one of the graphic representations of the diffusion data. The same data can also be displayed as a color-encoded texture map or, like we saw at the beginning of the video, with 3D tractography. Finally, I don't want you to be misled into thinking that diffusion tensor imaging provides axon-level resolution. Although I used an individual axon to demonstrate the concepts of isotropic and anisotropic diffusion, in actuality, the diffusion tensor represents axon bundles, with water diffusing through both the axon channels as well as the interstices between the bundles themselves. Newer but computationally intensive techniques such as diffusion spectrum imaging, diffusion kurtosis, and Hardy show promise as high-resolution tractography algorithms that may give us some anatomic insight into some of our most devastating neurodegenerative disorders such as Parkinson's and Alzheimer's, as well as post-traumatic injury to the neuronal fiber tracts.